Hello everybody, Victor from organicchemistrytutor.com is here, and in this video I want to look at the difference between the nucleophiles and electrophiles, what those species are, how to identify them in a reaction, and some common examples you are going to see in the organic chemistry course. So first off, let's talk about what the nucleophiles and electrophiles are to begin with. A nucleophile is a nucleus-loving species if we look at the word itself and translate its Greek roots. The nucleophiles are typically negatively charged or they have at least one electron pair that they can easily share to make a new carbon-carbon bond or carbon element bond or new chemical bond in general. For instance, if we look at CH3O-, the one that we have over here on the left, and CH3NH2 over here, then those species, the first one, the one on the left, is a negatively charged species, and it has the excess of the electron density, which means that it can easily share some of those electrons with electron deficient species and make a new bond. And the species on the right, while it's not a negatively charged species, it still has an electron pair that can be easily used to make a new chemical bond. So when it comes to electrophiles, though, the electrophiles are the complete opposite of nucleophiles, and they are the electron-loving species. And they are typically either going to be positively charged, or they're going to have a partial positive charge, or a delta plus if you like. In other words, electrophiles are electron-deficient species and are looking to get some more electron from somewhere else. And electrophiles will often have an electron withdrawing groups, and this is some sort of a group that's containing an electronegative elements that is pulling the electron density towards themselves. Or alternatively, the electrophiles can also have polarizable pi bonds, such as a carbon-oxygen double bond or carbon-nitrogen double or triple bond, etc. For instance, here I have a couple of electrophilic molecules. The first one has the carbon-oxygen double bond. This is a polarizable pi bond, and that puts a significant delta plus on the carbon, making it very electrophilic. The second molecule, I have the full positive charge on my carbon, and this type of a species we call carbocation, and carbocation is a 6-electron species. It only has 6 electrons around carbon, so it's very electron deficient since the carbon is lacking electrons from a complete octet. An important thing to remember about the electrophiles, though, is that they're going to be acceptors of the electron density in the reaction. They're always going to be acceptors. And by accepting some of that electron density from the nucleophiles, which are going to be the donors of said electron density, the electrophiles will be able to sort of quench their positive or partial positive charge, making a more overall stable species. So now, when we know what the nucleophiles and electrophiles are, let's look at a few examples and try to find those in each reaction. So in the first scenario over here, what I have is the reaction where the products and the mechanism is already given to us. And this makes our task much easier, as we simply need to follow the electron flow from one species to another species. And thus, if we see that the molecule on the left is going to be the acceptor of the electron density, that's the aldehyde functional group, because the overall arrow, if we look at our arrow flow, it goes towards our carbon from right to left. So the carbon in this case is going to be accepting the electron density, which means that the molecule overall is going to be the acceptor of electrons. And as an electron acceptor, we're going to classify it as an electrophile. While the molecule on the right, it has this electron pair. This is an amine molecule with an electron pair on the nitrogen. That is going to be a donor of electron density. It's pushing the electron density towards our carbon, and that's going to make our new bond. So if we look at that from the perspective of the bond making, nitrogen giving electrons to carbon will result in making a new bond. And here is our new bond between carbon and the nitrogen. And those electrons that are currently the bonding electrons, the electrons that are making this new carbon-nitrogen bond, those are the electron pair that used to be sitting over here on our nitrogen. Now, in the second scenario that I have here on the screen, we have the reaction products, but we do not have the curved arrow mechanism to show us the electron flow from one species to another species. So we'll have to figure out that one for ourselves. And so the question is, well, how exactly are we going to do that? And first of all, let's start by identifying the bonds that were made and the bonds that were broken in this reaction. Based on the structure of our product here, we can see that we have made a new carbon-oxygen bond over here, and we also broke a carbon-bromine bond, so this bond has been broken because now we can see that Br- is just floating in the solution by itself, and it's no longer bonded to anything. The next thing that we want to do after we have identified the flow of the after we have identified the broken and the made bonds, we want to identify the flow of the electron density in this reaction. And in this case, it is reasonable to assume that the negatively charged species is going to be our nucleophile, since it has an excess of the electron density. Generally, if you have a reaction between a negatively charged species and a neutral one, the negative ion will be your nucleophile. And likewise, if you are dealing with a reaction between a neutral molecule and the positive ion, the one that we call a cation, then the neutral molecule is typically going to have the higher electron density and will act as a nucleophile. So in this particular reaction here, the negative oxygen is going to be our nucleophilic piece, while the carbon attached to the bromine is going to be an electrophile. Remember, we already knew that we are making CO bond, so since we have identified oxygen over here as our electron donor, or a nucleophile if you like, we know that the carbon must be an electrophile because the reaction is always going to be going from nucleophile to electrophile. The bond is going to be always made by taking electrons from the nucleophile and giving those electrons to an electrophile and sharing those electrons with an electrophile. This is a very fundamental principle, and I know that I have already mentioned it before. Just want to make sure that this, fundamental principle kind of sticks in. Alright, so now the third scenario that we have over here is where we neither have products nor we have the curved mechanism for this reaction. So we'll have to figure everything out for ourselves. And this is perhaps one of the more common types of an exam question, so you are likely to see something like that on your exam or in your homework. So the first thing that we want to do here to figure out what's going on in our reaction is by finding all the electron density where you have the higher electron density, or delta minus or electron pairs in our molecules, and places with the low electron density, so something that contains delta plus or the positive charges. So identifying the electron pairs is fairly easy. We'll just check the element's position in the periodic table and then see how many bonds it has and add the necessary electrons to complete the octet. So for instance, in the case of phosphorus over here, we know that phosphorus is located in the 5th group of the periodic table, so it has 5 valence electrons, and already it has 3 bonds, so 3 of its electrons are being used to make bonds, so it means that the phosphorus has 1 more electron pair on it. Likewise, in the case of the chlorine, chlorine is located in the 7th group in the periodic table. It has 7 electron pairs, 7 electrons on it. 1 of that is already used for the bond, which means that we now have 3 more electron pairs sitting on the chlorine. So that part is fairly straightforward. Often, your instructor will already place all the electron pairs on the atoms in your molecules, especially early in the course, but don't count on that every single time. It's important to be able to do it on your own. So, how are we going to deal with the partial charges though? Well, partial charges can be a little bit trickier. Ideally, we need to look at the difference in the electronegativities between the carbon atom and other elements. And, well, naturally, nobody really expects you to remember the electronegativity values for all nonmetals. There is, however, a simple trick. So here I have a part of the periodic table with non-metals, and that you can normally see in the organic molecules. And in this, little piece, little triangle of the periodic table, I have highlighted elements in different colors. The red elements are the ones that going to add a significant delta plus on your carbon. The green elements, however, won't be able to polarize carbon sufficiently, so those bonds won't really do much for the electron density on the carbon in most cases. So whenever the carbon is bonded to something like nitrogen, oxygen, or your halogens, we can go ahead and place a delta plus on that carbon right away. And that's exactly what I've done over here by placing that delta plus on my carbon. When it comes to other elements, you're not going to put any positive or negative charges normally on the carbon, or partial positive or negative charges, so you'll just leave those as is. And after we have identified the places in our molecule with the electron surplus and the places with the electron deficiency, we now can easily assign the potential nucleophiles and electrophiles. So in our case here, it's going to look something like that. And here is something particularly important that I want to point out. Then whenever you have adjacent nucleophile and an electrophile, like what we have in this case with the CH3Cl, then those ones cannot at the same time be a nucleophile and electrophile. So it means that you'll have to choose whether your molecule is going to be acting as a nucleophile, or you're going to choose if your molecule is going to be acting as an electrophile. In this particular case, our left molecule can only be a nucleophile, which kind of a no-brainer. That means that our right molecule is going to be only an electrophile and not acting as a nucleophile any longer. So once we have identified our nucleophile and electrophile in the molecule, what we can do now, we can propose the electron flow from one molecule to another using curved arrows. And as nucleophile provides the electrons for the electrophile, we're always going to be showing the arrow going from the nucleophile towards the electrophile. In this particular case, we're going to be showing electrons going from phosphorus to carbon, because phosphorus is our nucleophilic species within the molecule, while the carbon is our electrophilic species within our molecule. However, we have a little bit of a problem here. If we look at our CH3Cl molecule, so we have carbon with 3 hydrogens attached to it, and we have one more chlorine over here. So if we accept extra electrons from the phosphorus, so here is my phosphorus with an electron pair, then by making this new bond, we are going to have a little bit too many electrons around the carbon. It's going to be 10 electrons, and the carbon cannot violate the octet. It cannot have more than 8 electrons. So as a rule of thumb, you always want to break a bond in cases like that to something that we call a better leaving group. And the leaving group is a type of a species that is stable, bearing a negative charge, or it becomes a neutral molecule upon dissociation. In this particular case, we can either break a bond to chlorine, like this, which is going to release Cl- into environment, or alternatively, what we can do, we can maybe break a bond to a hydrogen, which is going to release H- into the environment in our reaction. And if we compare the H- and Cl- as the two potential leaving groups, the Cl- is going to be a much more stable ion. And for the sake of time and staying on topic here, we'll discuss the ion stability and why exactly the Cl- is more stable than H- in another video. So to recap, what I just said here is that to accept the electrons from the phosphorus, we'll need to break the carbon-chlorine bond, which, by doing so, going to give us the products in this reaction. And we are done. Remember, the practice makes perfect in this case, and make sure that you go through enough practice problems identifying nucleophiles and electrophiles in various reactions and in various examples using these steps. You want to be able to identify the nucleophiles and electrophiles automatically by just looking at your molecule. You gotta train yourself up to that point, because normally this is going to be the first step in most of the reactions and most of the mechanisms that you're going to be dealing with in the scope of a a regular organic chemistry course, which means that if you're having troubles identifying your nucleophiles and electrophiles because you didn't practice enough, that will be, a huge problem from the very beginning. So make sure that you do enough practice so you'll be using this skill over and over again, and you want to make sure that this is a something that you can do easily. And while it's important to know the steps in identifying the nucleophiles and electrophiles in different reactions, most of the time you're going to see a lot of similarities from one molecule to another, from one reaction to another. And at the end of the day, organic chemistry is a science of patterns. So the whole ordeal with electrophile and nucleophiles is actually no different. There are some patterns that we can identify here as well. And as I have already shown you some examples of typical electrophiles and nucleophiles before, I'm going to show you a few more of those. And when it comes to electrophiles, they are typically going to have the following major features. The first feature is going to be very often the presence of a good leaving group. And our typical good leaving groups are going to be halides like chloride, bromide, iodide, or they can be sulfonate esters that have this structure. It's a big and ugly thing, but we're typically going to use three of those, which are triflate, mesylate, and tosylate. I'm not going to show their structures right now. We'll look at those at some later point, but those are also extremely typical and very good leaving groups. So whenever you have OTF, OMS, or OTS sitting on your molecule, you know that this is an amazing leaving group. Likewise, when it comes to electrophiles, we do very often have a very polarizable CO double bond. The thing is, when it comes to CO double bond, it has a very high delta plus on the carbon, which makes it into a perfect electrophiles. And you can have the CO double bond in such compounds as aldehydes or ketones, different derivatives of carboxylic acids like esters, acid chlorides, etc. When it comes to nucleophiles, though, the story is completely different. The nucleophiles are usually not bulky, so relatively small, negatively charged molecules like something with oxygen or carbon-containing nucleophiles or even halogens. All of those can be very good nucleophiles. For as long as the molecule is small enough, and for as long as the place in the molecule where you have that negative charge is not sterically hindered, so it physically can use those electrons to make a new bond, you're going to have a good nucleophile. Also, whenever you have neutral molecules, and if your neutral molecule has atoms like nitrogen or phosphorus or sulfur, all of those are fantastic nucleophiles as well. And generally speaking, whenever it comes to nitrogen, phosphorus, or sulfur containing molecules, you don't even need to have a negative charge. You can use molecule as is, and most of the time it's going to be a very good nucleophile going into your reaction without any kind of problems whatsoever. So now, I actually have a question for you guys. Do you have any of your own tricks on how you identify the nucleophiles and electrophiles? Let me know in the comments below. I'd love to know your tricks and your strategies. And please remember to subscribe, like, and share this video with all of your friends and classmates. I'll see you next time, and until then, remember to stay awesome!